Industrial hygiene, chapters 19 and 20, dilution ventilation and local exhaust ventilation control systems. The two major types of systems for controlling contaminants in the air. And now I want to make sure that there's a distinction between systems designed or intended to control contaminants as you might find in a workplace or an industrial setting versus a general ventilation system, which is common in a residential structure or an office building. The general ventilation systems are not specifically designed to control hazards in the sense of looking at releases within the workplace and controlling them. So it's a distinctly different, and that's why we talk about that next week in chapter 21. The two types for controlling dilution systems and local exhaust systems are basically designed to either dilute the contaminants down to a level where by the time it reaches the worker's breathing zone, it's safe, or in the case of a local exhaust system, remove them from the environment before they have a chance to get to the worker's breathing zone. The key point here is we're always looking at what is in the breathing zone of the worker and how can we ensure that whatever is in the breathing zone of the worker does not present a hazard or risk to that worker. Now, our dilution ventilation systems kind of have two major types. Natural ventilation. If you have a building, older buildings, if you look at them, they often have an extra little ridge across the top that has windows in it that can be opened. Those are designed so that as air heats up, it rises. And so you can get, with openings in the bottom and the natural ventilation, you can get things to air to rise and circulate just based on temperature differences. The other thing is most areas have prevailing winds, that is a direction that the wind generally blows out of, in which case you can open up that end of the building so that air blows into the building and then is forced up through and out the building. That's using natural forces to change those airs, get those airs to move, rather than our second system, which is a mechanical ventilation system. A mechanical ventilation system is one in which you use a mechanical device to move the air. It can be as simple as the old axial or propeller style fans, the fans that you might use to cool yourself off, or a box fan that you might use to cool yourself off, even in a residential structure, to very complex designs where they're bringing air at a certain place or taking air out of a certain place, and it's very much engineered and designed. There are some minimum requirements for those designs to ensure that the air clears out the contaminants away from the workers or by diluting it from the workers. And we'll talk about that in a little bit. The two main reasons to ventilate: health protection and fire and explosion prevention. Okay, we're either going to dilute it down to where it doesn't present a health risk, or we're going to dilute it down to the point where it does not present a fire or explosion risk. That's where our upper and lower explosive or upper and lower flammability limits come in, that we've been talking about in some of the other assignments. Now, dilution systems are designed based on some assumptions. One is the contaminant has to be released at a certain rate for us to do the calculations. So our release must be at a constant or near constant value, or my estimates will be off. And the other is that I can generate enough airflow through my system to dilute that contaminant to an acceptable level. Okay, and part of those assumptions that go into those calculations is I have to have complete mixing in the room. If I don't get complete mixing in the room, I have to adjust for that by adding more air to ensure that that unmixed air gets down to a level where it's safe before it gets to the breathing zone of my worker. I also assume that once I have my system in place, it's going to maintain the concentration below the level at which I want my workers to be exposed, whether it be the PEL or action level or some other standard. And we use what's called a K factor, or or as an additional safety factor, sometimes called a mixing factor because it also is often associated with the level of mixing that we have. That K factor is basically a multiplier to what my calculations say to ensure that the air volume flowing through the system is going to prevent my worker from being overexposed. Now, there are some circumstances where some of these assumptions break down. The main one is this one right here, the airflow through the system. We'll dilute it to, I can get that airflow. If my concentration of the chemical is very low, and it may require such large volumes of air, that I can't really deliver that. That's why when I use a dilution system, it's usually for contaminants that have relatively low hazard to them, both in terms of fire and explosion as well as health hazards. Now, this is not in your current textbooks. It's out of your old textbook. It used to be in the same chapter. And basically, it's looking at as air flows in, if I have a plenum, it kind of breaks up the air and gives it what we call a laminar flow, or the air flows kind of as a sheet, as opposed to turbulent mixing, which when it tumbles and mixes. I get a laminar flow out of that plenum. It flows across my worker. His work, where his exposure is coming from, is right here, and then it draws that air out. That gives me a mixing factor of 1, which means I don't really need to make a modification because it's pretty much going to ensure that I get that complete mixing and dilution that I'm looking for. Same sort of thing. Instead of bringing it from behind the worker, I'm bringing it from the ceiling, but it's the same route, the same sort of laminar exposure. If I don't get that plenum that breaks up my air, when I start getting a duct that's releasing it, I start getting a little bit of turbulence mixed in. So I've got to start adjusting that a little bit. If I'm just drawing the air from wherever, again, I'm going to get some turbulent mixing. I'm less assured that the air is going to flow across and away from my worker and its potential exposure. So now I'm starting to get a larger factor here. I'm starting to get a 2.5. Your current book breaks these into optimal, good, fair, and poor. The numbers are slightly different, so don't get too tied up in the numbers that you're seeing with these systems. This is really just to illustrate. That information has been updated. As you can see, this is originally from 1998, and your current textbook was published in 2013 with some updated information. Here's fair. I'm bringing the air in, but it's exhausting it from multiple points. I can get short circuiting, which is the air flowing directly from my inlet to the exhaust without really doing anything, or I might get turbulence or dead spots within my space. As things get worse and worse, you can see I started getting some really dead zones in this pore. In these dead zones, I'm still going to get diffusion and reduction just from having the airflow through the building, but it's not going to be very good, and I have to have a much higher adjustment to my estimated airflow to take into account the fact that I'm not getting very good flow. Some examples of how much airflow you might need. A welding rod, 330 seconds, which is a very small rod, still requires 1,000 cubic feet per welder. If you notice, they've actually modified these standards a little bit. For example, you can no longer use a gasoline-powered lift truck inside a structure. You have to use a propane or electrical. And oh, by the way, just because I have an electrical powered lift truck doesn't mean that there's no ventilation requirements. Those electric batteries can off-gas sulfuric acid, or not sulfuric acid, but hydrogen sulfide, as well as hydrogen, which can present a fire risk. So I need to make sure that if I have, especially in a charging area for my electrical lift trucks, that I have it properly ventilated. I've got to stick with those relatively low toxicity, relatively low fire hazard contaminants, because by definition, it's being mixed and my worker is going to get a certain degree of exposure. I don't want to expose him to something that has a highly toxic or even moderately high toxic property, because I don't want him to, over time, start showing health effects from that chronic exposure. So we're putting those fairly large safety factors in to take into account that some of our assumptions that are built into the calculations may not be 100% accurate, and therefore I need to bring in more air than I had planned on. I can use those dilution ventilation approach also for spaces that I traditionally consider confined spaces or enclosed spaces, as long as I ensure that, one, when I start diluting that air, I do not take something that's over the upper explosive limit, which at that point it doesn't present a fire and explosion because it's too rich to ignite. And as I dilute that down, I'm careful with how I handle that exhaust and that air in that space as it passes through the region in which it can ignite and explode. Okay. And also I need to make sure I'm monitoring for production of other materials, a lack of oxygen, and other things else. But by blowing that air through and diluting the air that's in those vaults and controlled spaces before my workers enter, I can reduce the overall risk that that atmosphere presents to my workers. I probably want to make sure that those workers still have a proper respiratory protection, based on what I think potentially they could be exposed to, but it makes it safer to make sure take some of those IDLH situations or fire and explosion situations away before my workers enter. Local exhaust ventilation systems, they're designed to capture contaminants at their source. They remove the material rather than dilute the material. They generally require less airflow than dilution ventilation systems, although that's not always true. With some particulates, you have to maintain the velocity of the air at a higher level than if you're, until it gets to the air cleaner and is removed, because you don't want those materials to settle out in your ducts. And if you get settling in your ducts over time, something like hitting the duct or disrupting that duct in some way can resuspend that material, and now you have a fire or explosive hazard within your duct that you did not anticipate. And I've actually seen systems, particularly with wood dust systems, where they did not do a very good job of maintaining their blowers and their air cleaners, which put a lot of resistance in the system, which slowed the air down sufficient for the dust to settle in the ducts, which later on ignited. Another example of that would be the Imperial Sugar in Georgia that blew up, I think it was 2011, maybe. My data on that is a little off, in which they had a series of explosions, because when they had one explosion, it suspended more dust in the air, which then ignited, which caused another series of explosions. So maintaining your system is really important. That local exhaust system consists of hoods, ducts, fans, and cleaner. In reality, you want your air cleaner before your fan so that your fan's not subjected to whatever nasty things that are coming through. For example, if you're collecting solvent vapors or that are organic in nature that can degreasers and things like that, it can take the grease right off the bearings on your fan, which then now your fan serves as an ignition source. Or if it's dusty air, it can plug up and damage your fan as well. You need to select the hood that's appropriate for the type of contaminant and where it's located relative to your worker. And we'll talk about those in just a second. And you need to make sure that your duct materials are compatible with what you are collecting as well, both in terms of reactivity as well as temperature. For example, you wouldn't want to use a metal duct if you're collecting acid mists and fumes, but you wouldn't want to use a plastic duct if you're collecting materials that are of elevated temperature that could melt or damage those ducts. Our three basic types of ducts: capturing hoods, enclosures, and receiving hoods. A capturing hood reaches out to kind of capture the contaminants. An enclosure is kind of your traditional lab hood that we'll actually show some of those later when we're doing our ventilation lab. But it's a hood in which you have enclosures. You reach into the hood space so that the contaminants are contained within that hood. And receiving hoods are for those materials, primarily particulates, where you're throwing the contaminants that have momentum to help them capture that material. A typical receiving hood would be on like a grinder or or a saw in which the materials coming off are going to have momentum in a predictable direction. It makes it easier to capture them. Another type of capture hood would be a canopy hood that you might put over, kind of a capture receiving hood that you might put over a vat where the process is hot, so it's natural for the materials to rise. And so you're receiving them because you're placing it there, but you're kind of capturing at the same time. And then slot hoods are slots, often in enclosure hoods, you'll have a slot in the back that helps make the flow across the hood face more laminar, which again helps keep the materials within the hood. And you don't get turbulence, because if you get turbulence at that face of those enclosure hoods, you can actually bring the material back out. So the air flows in, but since it's swirling, it comes in, it picks up the contaminant that's in the hood, and then it swirls back out because of the turbulence and turbulent mixing. Your ducts are there to carry the air between your other components, including a discharge stack. You need to have a discharge stack, because if you don't have that discharge stack and then a run of duct before you get to your fan, you lose a lot of energy at your fan, because if you have turbulence around your fan, it's not going to be able to move that air as well. Your ducts can be made out of a number of different materials. The key factor is you need to make sure that the duct material that you're using is compatible with the things that you expect your ducts to be carrying. Ducts, particularly where you have bends, elbows, and other things, you'll have turbulence. The turbulence, and then just the length of the ducts at the edges, you'll get friction, cause air losses and pressure drops across your material. If you have too much of these losses, the more of these you have, the larger and larger your fan needs to be in order to maintain the airflow through the ducts at the level you need it to be at. Fans basically come in two different flavors, centrifugal fans and axial fans. Axial fans, probably what most people think about when they think of a fan. The old propeller style fan where it turns and rotates. Axial fans do not do very well against pressure drops. And so most of the time, if I'm using an axial fan, I'm going to be using it for maybe an exhaust to blow the air out of a room, or blow air into a room for a dilution system, perhaps. I'm usually not going to use these very often for a local exhaust system, because I usually need a better pressure drop, which is what my centrifugal fans do. Most of the time with the centrifugal fans, we call those blowers. The air will come in and depart at a different angle. These are generally quieter. The forward curve fans are more efficient than the backward curve, but these guys are much quieter in their operation, which makes them a lot more acceptable a lot of times. But these can work against much greater pressure drops than these guys. Air cleaning, we've got particulate and gas and vapors, your typical particulate removal, filtration, which for some reason I left off, electrostatic precipitators that use the charge. Cyclones work in the same manner as the respirable cyclone that we used in the lab. Air comes in, it's got a spin. You've probably seen those. They look like round boxes that have a tapered bottom on them on top of industrial facilities. Basically, they use the impaction. They have the velocity of the air, the particles not being able to make the turn. They impact and fall and get collected. And then wet scrubbers, basically what you do is you mist or add moisture to the airstream, which then either condenses or absorbs the particulates. They get much larger, they fall out of the airstream, you can collect them. Gas and vapor removal, two basic mechanisms are adsorption and absorption. Both those, add and absorption. Add is adhering to the surface. The most common material used for absorption of organic materials is activated charcoal. It's got a very large surface area, so it can adsorb a large amount of material. The advantage of that is then you can take that material and then actually recover some of that if you wanted to. Absorption is when you bubble the material through a liquid of some sort that's going to react with or otherwise react and remove the material. Transfers it from that exhaust gas into liquid, and then you can use it for combustible dusts as well as gas and vapors burning, oxidation and burning, simply heating it up and burning it to reduce it to a non-hazardous material. Our basic airflow concept is the use of the equation of continuity. So the basic flow is called the equation of continuity, and basically it's the velocity of the air in feet per, in the US we use feet per minute. In Europe they use meters per second and cubic meters per second. The velocity in feet per minute, the area in square feet, so feet per minute times square feet give you cubic feet per minute. Okay. Now you can also estimate for a capture hood how far out into the room the air will reach, and that may be important depending on the distance between where your materials are or you expect they might go versus what your flow rate is. Now we don't actually do this in this class, it's a little advanced for you, but I wanted you to be aware of that you can calculate that. You probably want to talk to an engineer to get the numbers down perhaps, but that is a possibility to make sure that you're capturing what you think you are. Basic concepts about pressure. Static pressure can be positive or negative. Generally speaking, if you're on the suction side of the fan, it's negative, and if you're on the blowing side of the fan, as air blows out from the fan, it's positive. But with turbulence and mixing, you can get negative pressures inside a duct, even if it's on the suction side of the fan, or you can get negative pressures even if it's on the blowing side of the fan. You generally measure that with a device called a manometer. It measures the difference between the air in the room or your ambient air pressure and the pressure in the duct. Okay, so it's a differential pressure, so it can go negative. Velocity pressure is due to the air moving through the system. It represents the kinetic energy of the system. This can be considered maybe the potential energy of the system. Since it is related to the movement, the lowest this can go is 0. If the air is not moving, it's 0. If the air is moving, it's going to be some positive value. Now we're going to do this in lab in a couple weeks, measure the average velocity, and that's the velocity pressure is equal to the velocity divided by 4,005, or if you solve that for velocity, velocity is 4,005 times the square root of the velocity pressure. Okay, and then I can look at the total pressure in the system. That's simply the sum of my average velocity pressure and my average static pressure, or if I'm looking at a single point, the velocity pressure plus the static pressure at that single point. Total pressure can be positive or negative. It depends on how negative your static pressure is relative to the speed of the air going through the system. Velocity pressure is the only one that's fixed, always has to be positive. The other thing that we'll do in lab is calculate the air changes in a space. Sometimes we just want to know how rapidly are we changing the air out within a space. It's air changes per hour. And that's simply the volume of the room, the volumetric flow rate, which is feet per minute, cubic feet per minute. Now we're looking at air changes per hour. There's 60 minutes in an hour, and then divided by the volume of the room. And so I end up with a unit number of air changes, just some air changes per hour.